Hello everyone, my name is Ram and you are watching Group 10's Engineering Design Process presentation. Before we get into the challenges and niche aspects of our design process, I'd like to introduce our team. We are Team WALL-M. The name is a modified version of WALL-E, where instead of E for Earth, we have M for obvious reasons. I'm going to introduce our members now. In design, we have Charlie and Comic Sans Charlie. In electrical, we have me. In computing, we have Ryan and Chenan. And in mechanical, we have Nihar, Nathan, and Monish. 3 people, because we love mechanics. We as a team have been tasked with designing and building a prototype rover in order to explore solutions to the challenge of gathering building materials on Mars. Basically, our prototype will be assessed on how much regolith it can collect and deposit within a set time, how much energy it uses within that time, how cheap it is, and how appropriate it is for use in space. That last one is basically how modular and easy to transport it is.
Before generating ideas and concepts for designs of our Mars regolith project, a key requirement that had to be fulfilled was the identification of the problem. Basically asking ourselves the question, what are we finding a solution to? Without this crucial phase, we would possess incomplete knowledge about what our product's goals are relating to the problem brief, and hence have us developing ambiguous solutions to the problem. The development of our problem identification could then be used to delve into the objectives to be set for the project, which highlighted what our final product is supposed to achieve, considering the context of the project. Hence why the problem definition phase must be undertaken. The problem definition phase saw our team analyzing the problem brief and the key parts of the task assigned, which the product was supposed to fulfill. This can be observed through our team's tree diagram presented, which summarizes the applications of the product as well as the key characteristics of the product. A primary deliverable of this problem definition phase that we produced was the problem statement, produced to deliver a clear identification of the problem and the objectives of the final product, whilst disregarding any unnecessary subjective views. It also exemplified the clear gap between the project's current state and the final solution, and gave us a guideline as to what we wanted our product to achieve.
The initial development of the design statement involved clearly defining the objectives and constraints of the design, which is basically analyzing the design brief provided, which is generally more ambiguous, through different lenses, and this involves considering the who, the why, the what, when, and where. Where is it going to be used, what are the key specifications mentioned, and when is it going to be used, for how long. And so based on the information provided and sort of subdividing each of these aspects into clearer sections, we considered 3 important objectives that were imperative for our design. And so this involved energy efficiency, speed of delivery, and maintaining a compact size of our rover, where the speed of delivery was determined to be the most important aspect of our design. And so based on this objective, we need to have a way to measure the success of our objectives while also making sure that the constraints placed on the design are relevant and maintained throughout the project. And so just covering the several restraints that may be placed on the design was primarily done through research of journal articles and previous designs that other students have done. And some of the metrics were also used basically from paper sustainable metrics, which basically allowed us to consider what sort of metrics could be used to determine the power consumption of rovers, etc. And so using these novel and different methods, we figured it would be the best course of action to have a metric to measure 2 of them, because convectance is not quite tangible as a metric, and so it depends on the specific environment. And so hence, based on these factors and clearly defining the objectives and the constraints of our design, we arrive at the final design statement. And so the final design statement basically summarizes all of these aspects of excavating, transporting regolith on the simulated Martian surface and depositing them fairly efficiently, must be light and portable to reduce payloads, and this would be indicated using the power consumed within the former session using watts per hour, and the mass of the regolith collected per minute metrics, which basically gives us an indication of the productivity of our design, and hence we can clearly say that this is the problem that we are trying to solve.
The conceptual design phase really allowed the group to imagine a bit more and think outside the box, even doubt what was unfeasible. And without this design process, we wouldn't have known what components were like the most optimal and which design restrictions that we really had. And it really helped gauge our team's strengths and weaknesses through our own imagination and what field we could further specialize in to further develop the project. We then considered each major component of the rover, such as the movement, the regular collector and collection points, and even the types of motors, such as this barrel tank design, or this dumpster truck, a walking robot perhaps, automated vacuum cleaner, the ones that you find at home.
So the first concept generation tool that we used was the morph chart. So with the morph chart, we were able to show all the elements of the rover that we need to consider by sorting them into different rows. And in those rows, we were able to lay out all the potential options for each element of the rover. So the morph chart was essential for the next stage of our project design, which is brainstorming up here. So with brainstorming, each of us took different ideas from the rows of the morph chart and combined them in our own way. So each of us had really individual ideas, and we ended up with a lot of ideas, as you can see here. Here are a few. By paying attention to what ideas came up the most, like the excavator arm and also the loader arm, as well as what ideas were most unique, such as the brush and pan set and also the bottom trapdoor, we were able to come up with a design that was both innovative but also agreed upon by everyone. So our third and final method of concept generation was the 635 method. So how this worked is we each put forward 3 of our ideas from the brainstorming stage, and we put them forward and we had each other look at them and adapt them and morph them into something better, something more well-rounded and better suited to the problem. So this worked well. It allowed for a more innovative design, as we all contributed our own perspectives towards each other's designs, which let us tackle the problem from multiple different areas and angles, rather than just our own.
And now we have to ask ourselves, how can we achieve the best of our designs? Here we use the scamper method. So what can be substituted? The excavator head can be substituted for a load arm for more convenient transfer of materials. What can be combined? The load arm can be combined with a rotating brush to sweep the marble in. What can be put in other uses? It can be used to collect and transporting materials that's in dangerous environment, not suitable for humans. So we've accomplished so many designs and ideas for our OM, but after a range of discussion and evaluation, we have settled our design to be like this. We decided to use the loader arm as a collection method, the trapdoor to unload, and the 4 huge wheels to hover over the mountain ranges. By looking at it, there are positive aspects of the design, such as simple functioning loader arm that carries large quantities, and the trapdoor that can maximize the load without using a slope. However, this is still far from perfect. The loader arm may push away rocks from the platform. When it unloads, it could also cause congestion on the bottom of the truck. Yet, there can be still unlimited varieties where we can construct our design. So stay put, OM.
Hello, I'm back to conclude. When we initially faced this project, we quickly realized that we might have chosen the most difficult project in all of Desert 1000. But after listening to the lectures, we understood clearly that facing a complex problem requires us to break it up, analyze it bit by bit, and clearly define it. And that's what we did. With the hard part out of the way, we got to designing. In our initial stages of design, we wanted as many ideas as possible. And thus, we were totally uncritical of anything, no matter how absurd. From there, we began to criticize the possibilities, and eventually we narrowed our design down to a clear idea. From here, we plan on increasing our cooperation as a team, utilizing each member's specific strengths to progress on our prototype. We'll have regular meetings to keep everyone on the same page and ensure that our team spirit is high. No doubt there'll be many design challenges to go, and so in order to maintain our pace, we must always remain open to new ideas. Thank you for watching. Hope you enjoyed.